Houcine Dali here, who's been working with Massiege and other people, and he's continuing the series on Jack characters.
Thank you for the introduction, and thank you again for giving us the opportunity to give this series of lecture. So I will continue what Maciek started presenting last week. So Maciek in the first lecture presented some definitions and the main result about the main result of our paper about integrality and positivity in Lassalle's conjecture. And the second lecture, he presented the proof of the integrality part using the combinatorics of Lukács paths and some operators from some operators of Nazarov and Sklenin. So the three last lectures will be dedicated to the proof of the positivity in Lassalle's conjecture, and it will use a different kind of combinatorics related to maps. And it will also involve some other operators which connects Jack polynomials to maps. So the main idea will be to give a combinatorial interpretation of Jack characters using this family of layered maps that Maciek already defined in the first lecture, and I will try to recall the definition today. And this combinatorial interpretation allows us to obtain the positivity in Lassalle's conjecture. So I very briefly try to recall the definitions of the main objects in this story. So we have these Jack characters, which are basically functions on Young diagrams, and which give the coefficient of Jack polynomials in the power sum basis. And the main theorem is telling us that we can obtain the Jack characters as a sum of layered maps which have some phase type mu, and which are counted with some weights here. So there is this first weight which I will try to define today, which involves this statistic eta, which is a little bit complicated to define. And then there are other weights which are related to the layer structure of the map. So I'll try to define the second part of this lecture, all these objects. And actually, this formula is a kind of one parameter deformation of two known results about the characters of symmetric group for alpha equals 1. And for alpha equals 2, we obtain another formula for the zonal characters. And these two formulas were proved by Ferrier and Schneider in 2011 using representation theory. So the main tool to obtain this combinatorial interpretation of Jack characters is basically a characterization theorem of Valentin-Ferrier for Jack characters as shifted symmetric functions which satisfy some properties. So Maciek already gave this characterization in the last lecture, so I will try to recall this theorem and with a small example. So the first thing is that we study shifted symmetric functions, or more precisely, alpha shifted symmetric functions. So we say that a function is alpha shifted symmetric if it is symmetric not in the variables si's, but si's minus I over alpha, or I minus 1 over alpha. So the right way to define this is by defining polynomials in k variables in the si's, and then taking some projective limit of these polynomials. So now when we have a shifted symmetric function, we can think of it as a function on Young diagrams. So if f is a shifted symmetric function and lambda is a Young diagram, we can evaluate f in lambda by taking the si's equal to the lambda i's, and then just complete with zeros. And this actually gives an identification between the space of shifted symmetric functions and the subspace of functions on Young diagram. And the characterization theorem of Ferrier tells us that the Jack characters which were defined as functions on Young diagram, they are actually realized by shifted symmetric function. So if we fix mu, the character theta mu can be thought of as a shifted symmetric function, and this function is uniquely characterized by two other properties, which are a property of the top homogeneous part of the shifted symmetric function. So this part should be equal to a power sum symmetric function up to a normalization factor. And then the other property is a vanishing property, which says that theta mu vanishes on all the partitions lambda, which are smaller than the partition mu. So let me give a small example. So when we take the partition mu is just the partition 2, So the definition of the Jack character as a function on Young diagrams is we can compute it, and it's given by this formula. So it's just a sum over I, and it is some expression which depend on the parts of the partition lambda. So we want to prove that, or we want to check that this function as a shifted as a function in this infinitely many variables lambda i's satisfies the three properties of the characterization theorem. So we can first prove that it is actually a shifted symmetric function in the lambda i's. So this means that if we define the shifted variables as I primes, saying that f or this function is shifted symmetric in the lambda i's is exactly saying that it is symmetric in the shifted variables si primes. And with an elementary computation, we can obtain this formula, which is clearly symmetric in the si primes. So this gives the first property. The second property is the vanishing condition. So what we should check here is that this Jack character vanishes on partitions lambda of size less than 2. So we have exactly two Young diagrams, the empty Young diagram and just the partition 1. And we can just evaluate the lambda i's by the parts of these functions and obtain in the two cases 0, which satisfies the vanishing condition. And then we have this property of the top homogeneous part. So this function is shifted symmetric, but when we look at the top homogeneous part, which is the quadratic part here in the lambda i's, we obtain this formula, and this is exactly the power sum symmetric function P2 in the lambda i's. So now I will just a very brief context about the proof of this characterization theorem, which has been established by Ferré, and it uses theorems from Knoop and Sahi, which we already started discussing after the last lecture. So what this theorem of Knoop and Sahi says is that it's about shifted Jack polynomials, and they are defined as the unique shifted symmetric functions which have degree the size of the partition mu, and then which vanishes on all partitions lambda of size less or equal than mu, except for the partition mu itself. And in this case, we are just putting some, it's just some non-zero quantity. So the way we can think about this theorem is that we have a big linear system, which has as many equations as many unknowns. So, and the equations here are this evaluation of the shifted symmetric function we are requiring. And then we are looking at the space of shifted symmetric functions which have degree less or equal than the size of mu. So the dimension of this space is the number of Young diagrams with size less or equal than the size of mu. And this is exactly the number of equations. And this first part of the theorem is telling us that this system is a unique solution. But the more important, the more surprising part of the theorem is that this shifted symmetric function, when we look at the top homogeneous part, we obtain exactly Jack polynomials. So this is it was the first definition of shifted Jack polynomials given by Knoop and Sahi, and the second definition was given by Lassalle 2 years later, and which gives not shifted Jack polynomials as shifted functions, but as functions on Young diagrams. So when we fix a partition mu and we evaluate this J nu star in a partition lambda, we can obtain it by taking some derivation of the polynomial J lambda and then taking the scalar product against J mu alpha. And these two theorems allow us to construct an isomorphism between the space of symmetric function and the space of shifted symmetric functions. So this first part is, so we can send a Jack polynomial J nu into a shifted Jack polynomial J mu star. And this defines an isomorphism. And this isomorphism sends power sum symmetric function into Jack characters. And actually, when we use the two definitions of these two theorems of shifted Jack polynomials, this allows us to obtain the two definitions that we already have for Jack characters, first as a function on Young diagrams, and then as a shifted symmetric function, which is determined by some conditions. And actually, this duality is very interesting, and this is what we use in our theorem to prove the main theorem that I'm presenting in this lecture. So now we can think of these Jack characters as shifted Jack functions rather than functions on Young diagram. And we can have this slightly more general formula of the, or general version of the main theorem, which is saying that even when we think of the Jack character as a shifted symmetric function, we can still have the same formula in layered maps. So what I did compared to the first formula is just replacing the lambda i's by xi's. So just saying that the lambda i's does not have to do not have to be the parts of a Young diagram. So now what we want to prove is that this generating function of the right-hand side of this theorem, which is the generating function of layered maps, actually satisfies the three properties of the characterization theorem. So if you manage to prove that this combinatorial function satisfies the three properties, we will obtain by the characterization theorem that this is exactly the Jack character indexed by mu. And the advantage of this this characterization theorem is that now we do not really need to know what is a Jack polynomial. So all the properties of Jack polynomials are somehow encoded in this characterization theorem. So I will start a new section and try to define some, to give some definitions about maps. Are there any questions about this first part?
Yeah, can you go back one slide?
Yes.
Oh no, forward. Just
Sorry?
the last slide. Yeah, in this one, yeah.
Yes.
You have I running from 1 to infinity. Are these finite sums?
Yes. So actually, no, they're not finite sums. So because we have an infinitely many variables si's here. But what we can prove is that what we can see, since we are taking maps of a fixed size mu, so they will have a finite number of layers. But these layers, for example, if you assume that the map has k layers, these layers can be indexed from 1 to k, or from any integer n to from n to n plus k, for example. So the sum is not exactly finite, because we have an infinite number of variables on the left-hand side. But when we look at just a polynomial in k variables, the sum in the right-hand side is finite.
Okay, merci.
So maps. So the objects which appear in this combinatorial formula are maps. So I will try to define these objects and give some examples before moving to layered maps. So we start with connected maps. We'll say that a connected map is just a connected graph which is drawn on a surface, which might be orientable or not. So this is the first example of a graph which is drawn on the torus. So in particular, the torus is an orientable surface, so this map is orientable. And Maciek in the first lecture explained that maps, we can think of them also as graphs with a cyclic orientation around vertices. So what does this mean? We can draw this map without the underlying surface, just on the plan. And we can draw it as a graph, but this graph has a cyclic orientation around each vertex. So for example, if you compare these two maps, they have exactly the same underlying graph, but they do not represent the same map. And the reason is that the cyclic order around the vertex V here is not the same from one map to the other. Because here, when we turn in this direction, we see the vertices E1, E3, E2, while here it's E1, E2, E3. And actually, we can do the same thing for non-orientable maps. So we have here an example of a map which is on the Klein bottle. So here, the square represents the Klein bottle, and the graph inside the square is the map. And we can do the same thing. We can represent non-orientable maps with graphs with cyclic order around vertices, except for the fact that now we allowed some edges to be twisted. So here we have what we call a ribbon graph. So this is a graph where the edges are somehow a little bit thick. So some of the edges can be twisted at most once. So we have the square here, the outside square. It has 4 edges which are not twisted. And we have here this edge which is twisted exactly once. And since representing ribbon graphs is a little bit complicated, we can simplify the representation by just putting some crosses on some edges to remember that these edges are actually twisted. And the only problem of this representation is it is not unique. For example, we can check that these two maps, these two representations correspond to the same map. So I will try to explain how these representations are obtained. So the original definition is a graph which is drawn on the surface. And to have this planar representation with a graph, what we have to do is to choose a side for each vertex on the underlying surface. So let's take this vertex V, for example. It's drawn on the surface, and we have two possibilities to represent it. We can represent it from this side 1 or this side 2. And since the underlying surface is not orientable, we do not have a canonical way to choose a side. For example, like orientable surfaces have always an exterior side and interior side. So we can decide to represent all vertices from the same side. This does not exist in the case of non-orientable surfaces because we do not have the notion of exterior sides. So we'll choose a side for each vertex. And if I change the side from which I represent the vertex V, we will pass from this representation to this representation. And in this kind of in this change of sides, the operation that we are making is to switch to exchange twisted edges with non-twisted edges. And then the second operation is to change the cyclic order in which we are reading edges. So for example, here the twisted edge is E3, while here it's maybe there is a problem with this representation. I think that E3 should not be twisted, while E1 and E2 should be twisted because we exchange them. And then we also change the cyclic order. So we do not read E1, E3, E2 in the direct orientation, but E1, E2, E3. So this was the definition of a connected map. So more generally, a map is a collection of connected maps. And we will say that the map is orientable if all the connected components of the map are orientable. So for example, the map obtained by these two connected components is not orientable because it has one orientable connected component and the other component is not orientable. And a last definition, so as Maciek precised in the first lecture, all the maps that we are using will be bipartite in the sense that vertices have two colors, white or black, and each edge connects to the vertices of two different colors. And when we have a map, we can assign to it some statistic. So the first natural statistic is the size of the map, which is here the number of edges. And so when you have a map, we have a notion of, so they have the white vertices, black vertices, but also this notion of faces, which are obtained by traveling along edges. So each time we can define faces as the cycles obtained when we travel just following the corners of the map. So in the first example here, we have an orientable map, so which has 3 faces, and we can assign to each one of these faces a degree, which is obtained by taking the number of edges divided by 2. So for example, here we have a face of degree 4, and since the map is bipartite, its degree is always even, we can divide it by 2. And when we take all the degrees of the faces and divide them by 2, we obtain a partition which is the same size as the size of the map. So here the map is of size 5, and the face partition is also of size 5. And we will call this partition the face type of the map. And you can do the same thing for this second example, except that since some edges are twisted, when we travel along a twisted edge, we when we enter here, we get through the edge and we go out from the other side. And that's the only difference between orientable and non-orientable maps. So the last definition about maps is
Sorry, what was the face type of the second map?
Yeah, so if I'm not mistaken, it should be okay. I think that this is okay. This is wrong. Sorry, it should be 5 because we can try to construct the
Thanks.
the faces. So we can start here, for example, and then we will follow the corners of the map, and we arrive here. So we'll get through this edge, and then here we have a second twisted edge. So we are in this area, and then we just go out here, and we go back exactly to the starting point. So this face has exactly one, this map has exactly one face. So this face should be of degree 5. I'm sorry, this should be, yes. Thank you. So last definition is this notion of layered maps. So these are maps with an extra decoration. So how to define layered maps? We first assign labels to black vertices. So if the map is k-layered, we can use labels from 1 to k without any condition. So a label can be used many times or 0 times. And for example, here we have this label 1, which is used twice. And once we fix the labeling of black vertices, we can assign labels to white vertices. And so to each white vertex, we look at all its neighbors and we pick the maximal label among them. So we have here an example of a white vertex, which has 3 neighbors labeled by 1, 1, and 2. So we pick the maximum label, which is 2. And more generally, we say that a map is layered if it is k-layered for some positive k. And finally, we have this definition of labeling for layered maps. So we say that a layered map is labeled if for each layer, so if we fix a layer I and a degree j of black vertices, will require that the black vertices in this layer and with this degree are numbered from 1 until the number of so from 1 until the number of vertices satisfying this condition. So let me give an example. So if you look at for I equals 1 and j equals 3, so we have 2 black vertices in layer 1 and with degree 3. So these vertices are numbered by 1 and 2. So it's just an order on vertices in the same layer and with the same degree. And actually, this definition will be useful to decompose map later. And the second condition is that each black vertex has a marked oriented corner. So these are the arrows that are drawn in brown. So this finished the definition that I wanted to give about maps. And there was one missing definition to understand this combinatorial formula of Jack characters is this statistic eta, which appears as the power of this shifted parameter B. And these statistics are called statistics of non-orientability and were first defined by Goodman and Jackson in the context of a B conjecture, which is another conjecture relating Jack polynomials to enumeration of maps. So how are these statistics of non-orientability defined? So here we are looking at statistics of non-orientability on this class of maps, which is given by layered maps. So we say that a statistic is a statistic of non-orientability if it assigns to each map a non-negative integer, with the only condition that this integer should be 0 if and only if the map is orientable. So now we have this shifted parameter B, which is obtained by taking the Jack parameter alpha and then shifting it by 1. And in all the generating series that we will consider, we will count maps with a weight B to the power of a statistic of non-orientability. So why is this interesting? Because when we take alpha equals 1, this statistic, this weight, related to B will give exactly 1 if M is orientable, and otherwise it will give just 0. And when we take alpha equals 2, so this means that B equals 1, and the weight will be will give 1 for any map. So now when you, if you take out the main formula, the combinatorial formula of Jack characters for any alpha, and we take alpha equals 1, we will exactly have the orientable maps on the right-hand side of the formula. And when we take B equals 1, we'll have all the maps. So, and this corresponds exactly to the theorem of Fourier-Hachiniade about the characters of the symmetric group and the zonal characters. So are there any questions about this definition? Okay, so this definition is very useful to define generating series which are deformed, which are a deformation of orientable generating series and non-orientable generating series. The only problem of this definition is it does not tell us how to construct such statistics of non-orientability. So here I will try to explain the general method to obtain such statistics. And this method has been used in many different works relating Jack polynomials to maps. So if we take a map of size n, in order to define to define statistics on orientability, we should choose a decomposition algorithm for all maps. And this decomposition algorithm is just a linear order on all the edges of M. So this is basically saying that there is a first edge E1, the second edge E2, and when we decompose the map M, we will start by deleting the edge E1, E2, and so on. And we will denote by MI the map obtained by deleting the first I-1 edges. So this is the first step. The second step is to define some statistic on pairs of map and edge. So if M is a map and E is an edge of this map, we have some statistic, kind of oracle, which tells us if theta of ME should be 0 or 1. And this statistic should be understood in the sense that it is deciding whether this pair of map edge is a good pair or not, in the sense of when we add the edge E, are we going to increase the non-orientability of the map or not? So if you decide that adding the edge E does not increase the non-orientability of the map, we will assign the statistic 0. Otherwise, we will assign the statistic 1. And then we define the statistic eta of the map M as the sum of all the statistics theta collected while decomposing the map edge by edge. So the second step was more or less the same in all the previous works. And this is exactly what we will use in the case of layered maps. And it's the first step which varies from one model to the other. So I will start by explaining how to define this statistics theta, and I will explain later what decomposition algorithm we use on layered maps.
So this eta is independent of the total order if you choose?
No. This is the kind of properties that we like to have, but this is not true. And actually, the total order that we choose is very important to have So in particular, in our case, in the combinatorial formula for Jack characters, if you do not use the right decomposition algorithm, the statistics eta obtained do not work for the formula. I will explain this in more details in a few minutes. So in order to decide if adding an edge increases the orientability of the map or not, we should have a classification of edges. And we can ask the other question. So if we start from a map of size n, and we would like to obtain a map of size n+1, in how many ways we can add an edge. So this first simple way is by saying that we will just add an isolated edge. So this means that we will add a new white vertex, a new black vertex connected by an edge. The second way is to add one, I think this is the opposite. Okay, so in this case, we add a white vertex on a black corner. So this corresponds to this picture. We choose a black corner of the map and we attach to it a white vertex. We can do the opposite. We add a white black vertex, a black leaf or a black vertex on a white corner. So this is the second picture. So these are the three ways to add an edge using some new vertices. But we can also add an edge without using some new using new vertices. So how we do this? We just choose two corners of the map which have two different colors. So let's say C1 and C2, and then we will connect them by an edge. And since we are using, we are allowing non-orientable maps, we have always two possible ways to add such edge. So if I call E the first edge, the second edge E tilde will be obtained by twisting E. And we will say that the two edges are associated. So we can pass from one to the other by a twisting operation. And for all choices of C1 and C2, we always have two ways to add these edges. Except that we can imagine some symmetries problems. So I took here the simplest examples of for which we have symmetries. So we imagine that the initial map is just this map of two isolated edges. So the edges which are represented in black. So if we imagine adding an edge E connecting these two corners and then twisting it, actually the two maps obtained are the same. Because we can pass from the one on the right to the one on the left by making a twisting operation. So if you twist this E, we still have the same map. Except that this is not actually a problem in our case because all the maps that we use are marked. So they have this marking on black vertices. So what does this mean is that in the first connected component, we have at least one black vertex. And with this labeling definition, this black vertex has one marked oriented corner. And the same for the second connected component. And with these marked corners, even when we twist the edge, the edge E, we do not have the same map on the right. So this is actually a usual trick when we work with maps. We do not really like symmetries. So we always mark at least one corner in each connected component to avoid this kind of problems.
Sorry, I just want to make sure I understand. So are all the black vertices marked?
Yes, yes. So
Okay.
this is related to the definition of vertex labeled
Right.
layers.
Mhm.
Labeled layered maps. So we have layered maps. So each black vertex and white vertex has some layer from 1 to k. But in addition to that, the black vertices are labeled in the sense that we have a total order on black vertices which are in the same layer and with same degree. So this is the second line. And the first line is to mark one corner in which black vertex.
Okay.
So here we have 4 black vertices and we have 4 marked corners.
I see. Thank you.
And actually, these are the four ways to add an edge on a map of size n to obtain a map of size n+1. So this allows us to have a classification of edges when we have, if you do the opposite, we have a map of size n+1 and with a marked edge, and we will remove this edge. So we have the first 3 cases where the edge uses new white vertices. And actually this operation of adding an isolated edge for a black leaf or a white leaf, they do not increase the complexity of the map. So if we imagine, for example, that the map M is orientable, by adding such an edge, the obtained map will also be orientable. So we will always assume that the statistic theta obtained by assigned for this pair is 0. She's saying that the edge is actually good. It is an orientable edge. So now we have this second or the fourth case in the previous slide, the case where we add an edge without using new vertices. And in this case, we will also distinguish many cases. And this case depends on the relative position of the two corners C1 and C2. So here in the first case, we are adding an edge between two corners in the same face. So we have two possibilities to add such edge. And in the first case, by adding the red edge, we formed from the starting face two faces. So we have a face here and a face here. While in the second case, we started from this blue face and we also obtained one face by the end. Because when we are traveling along the face and we arrive to this edge, we cross it and we are on the other side. So we can imagine that the first edge looks orientable, so give it the weight 0, while the second one is non-orientable, so we'll give it the weight 1. So here we have a second case where we are adding an edge between two corners in two different faces, but the two different faces are in the same connected component. So here we have a corner in this face F1 and a corner in the face F2, but F1 and F2 are in the same connected component. And in this case, we say that the added edge is actually a handle. And in this case, actually, it's difficult to decide whether the edge is orientable or not. So the only condition, so the first condition is saying that even if we cannot decide whether E is orientable or tilde is orientable, we just decide that exactly one of them is an orientable edge. And this is translated by the condition that the sum of the two weights is 1. Which means that exactly one of them is 0 and one of them is 1. There is only one case in which we can decide for sure which edge is orientable and which edge is not orientable if the starting map is orientable. So in this case, by adding a handle, there is exactly one of the two handles which give an orientable map, and the other one will give a non-orientable map. And in this case, also, it is easy to decide because the orientable map should have the statistic 0, and the non-orientable map should have the statistic 1. And the last case is the case where we are adding an edge between corners in different faces, but these faces also have are in different connected components. And from a geometric point of view, adding such an edge, which is called a bridge, is taking some sum of two surfaces, is gluing two surfaces. And such operation do not increase the non-orientability of the surfaces. So we'll always decide that a bridge will have a weight 0. Sorry. Yes. So
I have one silly question. So in the second case, maybe the next case. Yeah.
Yes.
What if your M was non-orientable?
Yes. So if the M was non-orientable, this is the hardest case because M is already non-orientable and we have two faces in the same connected component, and it's hard to tell which edge is orientable and which edge is not non-orientable. So this is given just by the first item. So we do not decide.
Okay.
Decide whether which one is good or which one is not good. So we just require that the sum of the two statistics is 1.
Okay.
And in particular, so this is a very good question because of this condition, which is we do not have a unique statistic of non-orientability.
Okay.
We have an infinitely many statistics of non-orientability, but we'll see later that they are all equivalent in the model of maps that we are looking at.
Thank you.
So now the second question, so this gives us a statistic on a pair of map with a marked edge. And the second question is how to decompose a map. In our cases, we have layered maps. So we have a map like this one, and we would like to define an algorithm which decomposes this map. And I think that the more natural answer is to decompose it randomly, which means that we are taking, we'll take all the possible linear orders on the edges of the map, and make all the decompositions, and at the end takes a kind of average. And this is this idea was used by Doinga, Ferré, and Shinade in 2014, and they proved that when we are working with one layered maps, this is a good answer. So the statistics obtained, they give Jack characters, but just for one layered maps. So this in terms of partitions, it corresponds to Young diagrams which are rectangular. But in the paper, they also provide a counterexample for maps which have more than 3 layers. So they prove that for some partition, Young diagrams of size 9, and in the case of at least 3 layers, this statistics does not work for Jack characters. So which means that the combinatorial side of the equation does not correspond to the algebraic side of the equation. So we use a different kind of decomposition algorithm, which uses the structure of layers of the map. And more precisely, we'll decompose the map in an increasing order of the layers. So each time we decompose the map, the layer of the smallest index. So here we have 3 layers of indices 1, 2, 3, and we will start by deleting all the vertices in layer 1, and then 2, and then just 3. And in this operation, we'll start by decomposing the vertex of maximal degree and maximal number. So let's say that here we have in the layer 1 2 black vertices, which are in layer 1 and which have the degree 3. So in order to decide with which one we start, we'll start with the one with the maximum, the maximal number, which is this one, which is numbered by 2. So we delete this black vertex, and then we delete this black vertex. And in this operation, we start each time by the marked corner. So if you remember in the definition of labeled layered maps, each black vertex has this marked corner. So we start with this black vertex and starting from this oriented corner. And then we will delete the second black vertex from this marked corner. And the idea is that, so this gives us this order for the first layer. So we start with C2, we delete the first edge, the second one, third one. So by the end, we deleted all the black, this black vertex, this block of black vertex of degree 3, and then we restart with the second black vertex. And the idea is that by the end of the operation, we don't have black vertices in layer 1, but we also don't have white vertices in layer 1. So if you remember, we had one white vertex labeled by 1, but this vertex is necessarily connected only to black vertices of in layer 1, because by definition, white vertices are in the maximal index of layer of all the black neighbors. So they cannot be related, for example, to black vertices in layer 2 or 3. So by the end, we only have vertices in layer 2 or 3, and we can restart with layer 2. And until having just an empty map by the end. So are there any questions about this decomposition algorithm? And actually, it gives all the definitions that we want to define the generating series of layered maps with this. Maybe I can explain this on the formula. So here we are taking the sum over all layered maps with phase type mu. So we have many normalization factors, but there are two important weights. So there is this non-orientability weight, which is of the form of the shifted parameter b to the statistic of the to a statistic of non-orientability.
Can I just ask a question, if you don't mind?
Yes.
So you explained how to delete the vertices, but what you were really looking for was to give some ordering on the edges. Did you explain that?
Yes, yes. So when I say that we are deleting the edges, so this means that this is the first edge, because this is the first one that we delete. And then this one is the second one, because this is the second one we delete. So the total order on edges is just the order of decomposition.
And,
So,
you actually pick the corner and direction, so it's not that, so you know which edge is first and which is second and so on at each black vertex.
Exactly, yes.
Okay, thanks.
The reason we know which is the first black vertex because we have this labeling. Because if we have layered maps which are not labeled, that would be hard to pick which black vertex to start with, for example.
Yes.
So in this definition, I think that there are two important things that we are decomposing in this total order on edge. We start always with layer 1 and then layer 2 and so on. And the other important property is that even within the same layer, we are not decomposing the edges randomly. So we have this structure that we are turning around black vertices. What is not very important in this second point, that we are deleting them in starting each time by the vertex of maximal degree. So you can imagine, for example, if you have three vertices of degrees 1, 2, and 3, we can start by the vertex of degree 3, and then 1, and then 2. So the order on the vertices is not important. It's just a way to say that we have a canonical order to delete all black vertices following this cyclic orientation around them.
Thank you.
So this gives this definition of statistics of non-orientability, which is in green here. And we have also another important weight in this formula, which is the weight related to the layer structure, which is saying that, so here we have minus alpha Si. So Si is the ith variable of this infinite alphabet Si's. And we are taking minus alpha Si's to the power of white vertices in layer I. So what we are saying is that to each white vertex, we assign minus alpha times S indexed by the layer of this white vertex. And then we take the product over all white vertices to obtain this blue weight. And here there are some normalization factors. So for example, this normalization factor, in this partition mu black I is the partition which gives the degrees of black vertices in layer I. And this is directly related to the fact that we are using labeled maps. So this is the kind of normalization that we have in the exponential generating functions, except that here the labeling is not just, it depends on the degrees, which explains that we have this Z factor instead of the usual factorial. And this factor is a little bit more tricky, and I will explain it maybe the next lecture. So I said that we'll try to prove that this generating series of layered maps satisfy the three characterization theorem of the three characterization properties. And actually, there is always a first or a condition 0 to check before checking the shifted symmetry property, the top homogeneous property, and then the vanishing property. It is stability property. So the stability property is when we define the generating functions of k-layered maps. So we have functions or just polynomials in k variables S1 to Sk. And then you can take the sum over all layered maps with k layers. And what we want to check is that this sequence of functions actually satisfy this property that when we take the function dx by k plus 1 and then evaluating the last variable in 0, we obtain the function just in k variables. And this property is important if you remember what Maciek explained last time, that this is important to check that the sequence of f mu k's define a projective limit over k. So let's check this property. What is this left-hand side? So this is a sum over k plus 1 layered maps with the condition that this weight of white vertices in layer k plus 1 is 0. So this corresponds to k plus 1 layered maps which have no white vertices in layer k plus 1. But actually this also implies that the map has no black vertices in layer k plus 1. Because if you imagine that there is one black vertex v in layer k plus 1, by definition, it should have at least one white neighbor. But this white neighbor will take the maximum label among all its neighbors. And since k plus 1 is maximal, this white neighbor will have label k plus 1. But we know that this is not possible, and this proves that the map does not have any vertex in layer k plus 1. In particular, this layer is empty, and this just corresponds to a k-layered map. So, in particular, we know that this sequence of f mu for a fixed mu, the sequence of f mu k's defines a projective limit. So we can try to check the three properties of the characterization theorem on polynomials in k variables. And if you check it for any k, so we have the properties in the projective limit. So let's start with the first condition, which is related to the top homogeneous part of the shifted symmetric functions. So if we fix a partition mu and an integer k, we want to prove that the top homogeneous part of this polynomial in the SIs corresponds to the power sum symmetric function p mu in these variables. So what does it mean to take the top homogeneous part in this formula? So it's top homogeneous in the meaning of the SIs, but to maximize the degrees of the SIs corresponds to maximize the number of white vertices. And we can check that in order to maximize the number of white vertices, knowing that we are fixing the size of the map because you are fixing the face partition mu. So maximizing the white vertices means that for each edge we should have one white vertex. So in other terms, all white vertices should be leaves or white vertices of degree 1. And this corresponds to these star maps, which are centered in black vertices, and all the leaves are white. So in particular, here we are fixing the face type 3, 2, 2 for in this example. What we can prove is that the face type also corresponds to the type of black vertices, which means that for each face we have exactly one black vertex. So this partition of black vertices corresponds to the partition of faces, which is exactly the partition mu. But also these maps are just orientable. So from the definition of statistics of non-orientability, we say that we know that the associated statistic should be always 0. And then the last quantities that we would like to understand is the number of black vertices and the number of connected components. But we know that a connected component is associated exactly to one black vertex, and one black vertex is associated to one face. So these two quantities are equal to the length of the partition mu. So in particular, this big quantity here is just given by this -1 to the power size of mu times alpha to the power of minus the length of mu. So for now, we do not have this layered structure in this definition. So just know that the maps which are involved in the top homogeneous part should be these star maps. So after choosing the map, so this is exactly one map like this, and now we'll pick a layer for each one of them. So if we decide the layer of the central black vertex here, this will decide the layer of all the white vertices. So this layer weight here, given by the product of minus alpha si's, if we decide that this black vertex is in layer 1, for example, we will have the power, the weight minus alpha s1 to the power 3, because we have 3 white vertices. And we can do the same for the other stars. And each time the weight that we obtain is just the sum of si to the power, the degree of the black vertex, with some power of minus alpha. And when we take the product of all this, we have this power sum symmetric function in the si's. And then there are some renormalization which is related to the labeling, because we want to have this labeling of layered maps. And when we put everything together, we obtain that the top homogeneous part of this generating function is just the power sum symmetric function indexed by nu up to a normalization factor. And this finishes the proof of the first property of the characterization theorem. And actually, this is the property which is easy to check combinatorially without differential operators, which will not be the case, unfortunately, for the 2 other properties, and they will require some constructions with differential operators that I will try to explain the next time. And I think that I will stop here. Thank you.
Thank you so much. Any questions? I don't see anyone asking. I mean, I always have different questions, but yeah, okay, you can unmute and ask.
Oh, sorry.
Yeah, sure.
I mean, if somebody else wants to ask a question, then, I don't mind waiting.
No. Go
Sorry,
ahead.
so it was still just the same question. At each vertex, you've chosen an oriented corner, so that's some cyclic orientation on the edges.
Mhm.
Is the non-orientability, does it only depend on the cyclic order, or does it depend on actually what's 1, 2, 3, etc., each edge?
So I think that, so you mean the statistic that we'll have by the end?
Yes.
Yes, so actually it will depend on everything. So for a fixed map, if we change the labeling, if we change on which corner we are routing, the final statistic will change. But
No. So, I mean, there was 2 things, right? So I'm still trying to get my head around this, but so you put the vertices in layer, and then there's degrees, and that decides in which order you pick the vertices. Now, but once you've picked a black vertex, what you have is some marked oriented corner. Okay, but if you change if you just sort of move from one corner to the next corner in this orientation, does that change eta?
so
Right. If you flip, so in other words, does it just depend on the cyclic order, or does it actually depend on what's first in the cyclic order? Is it like a cycle?
I think it depends on which is first in the cyclic order.
I see. Okay.
Because I think that there are even some small examples for just with maps with 3 edges. And
Yes.
when we change the first edge with which we start, the statistic at the end will change.
Okay. So in your case, when you've marked a corner, you start with the first edge that's at the end of the corner or at the beginning of the corner?
Actually, this is not very important. So it's important to fix the convention, but we can use one convention or the other. And by the end, the result will be the same. So maybe for one map, the statistic will be different, but the final result will still hold.
Yes, because you could always change that, right?
Exactly, because we sum over all labeled maps, and we will whether we use one convention or the other, we have the same sum.
Thank you.
However, if we do not respect this layer structure, even when we sum over all maps, the statistic by the end may be wrong, in the sense that it does not correspond to Jack characters.
So seems like no other questions. Then let's thanks the speaker again.
Thank you.
Thank you. So we'll resume on Thursday at noon again. All right.
Okay.
Bye
Thank you.
everyone.
Bye.
Bye bye.